This is part 2 of the Module 9 lecture. And here we're going to learn our first method for this module, which is comparing the variance of two independent populations. And this first part corresponds to section 12.1 of the textbook, where they show you how to use table 7, the table of F probabilities. So this section of comparing variances is really not covered by the textbook, but it's an important technique to learn because you need this in order to select the appropriate method to compare the means of two independent populations. All right, so now I'm going to be using this diagram to highlight what technique or what method we're going to be learning. So in this first phase, we're comparing two independent populations, and we're going to learn to compare the variances of these two independent populations. And notice one thing, we're talking about variances, not standard deviations. So if you, in a problem, you get a standard deviation, please remember to square that quantity so that you get the variance. All right, so why do we need this? Well, two general uses of this test is that of when you're improving a process. And normally when you improve a process, you want to demonstrate that the variability of the new process is smaller than the previous variability. So in this case, the objective will be to show that the variability before the process is improved is higher than the variability of the process after it's improved. Or in this case, we want to show that the variance before is larger than the variance after. Another very important application is to determine if the variances are equal so that we can select the correct method to compare the means of independent populations. So you either have this situation where you have two populations that are identical except for their location, that is, their means are different, or you may have this situation when you have two different populations or two different distributions with different standard deviations and different means. All right, so this is how you would run into comparing two variances. To compare two variances, we need to use the F statistic. And F statistic is the ratio of the sample variance to the population variance for the first population to the ratio of the sample variance to the population variance of the second population. If you do the algebraic arrangement, you end up with the ratio of the sample variances and in the numerator and the ratio of population variance in the denominator. All right, so if these are random samples, that means each sample has independent observations. And these samples are taken independently from two normally distributed populations. The F statistic then follows an F distribution with two sets of degrees of freedom. So the degrees of freedom in the numerator, and that's a sample size of the variance in the numerator, -1. And the denominator of the denominator degrees of freedom, which is the sample size of the variance, the second sample variance, in the denominator right here. Okay, so it's very important to keep track of which variance is in the numerator and what variance is in the denominator, because then that's how you're going to associate the degrees of freedom. All right, and if you notice all these quantities, all these variances are positive quantities, so the F values are positive. So the F distribution only shows you positive values that start at 0 and then go on to the right of the scale. And these F distributions are positively skewed. And they are completely determined by the degrees of freedom in the numerator and the degrees of freedom in the denominator. And as you can see in this figure, I'm showing you all these combinations of all these F distributions for these combinations of degrees of freedom in the numerator and the denominator. All right, so now the next step is, well, how do we get probabilities for these F distributions? Well, this is becoming a difficult problem because now you have an infinite number of F distributions, one for each pair of degrees of freedom in the numerator and degrees of freedom in the denominator. So table 7 shows you values to the right of an F value. And let me switch over to the table. So table 4 consists, or rather table 7 consists of 4 tables, one for a probability of 0.01, one for the probability of 0.25, the probability of 0.05, and 0.1. And then each of these 4 tables is for one probability, and it shows you at the top the degrees of freedom of the numerator. So those are the column headings, and the row headings correspond to the degrees of freedom for the denominator. So make sure that you print this table, because we're gonna be using it in this section. So if you haven't printed them, stop here, go print them, because we're gonna use them in an example. All right. So, and table 7, as I say, shows F values, and we're going to designate the values to the right as F sub A, degrees of freedom of the numerator, and degrees of freedom of the denominator, and that corresponds to probability to the right. For F values larger than this value, and the probability is equal to A. And that for each pair of degrees of freedom, as we saw on the table. Now, sometimes, for example, when we do a two-tailed test, we're going to need the lower F value to designate the lower rejection region. And so in that case, we are looking for this new value on the lower end. And notice that I'm using a different designation for that F value. I'm using 1 minus A, degrees of freedom of the numerator, and degrees of freedom of the denominator. I'm making that stressing that difference, because this is not a symmetric distribution. So even though I have the same probability to the right, that's one number, and for the same probability to the left is a different number from this number up at the top. So we make that distinction. If these subindices cause you trouble, then call them F lower and F upper, for example, or F high and F low, whatever works for you. But just make sure that you know that these two numbers are different, because this distribution is not symmetric. So to find the lower value, we just use the inverse of the upper value. So from the table, you find the upper value, and once you have that value, then to find the lower value, you just take the inverse of that value. All right, let's look at an example. Now, so in this example, they're asking us to find the lower F value from an F distribution with a probability A of 0.025, with numerator degrees of freedom 4 and denominator degrees of freedom 9. All right, that means that you need to go to the table, go to table 7 and find the sheet where you have the probability of 0.025. So in here, then this is a probability of 0.01, so we need to go to this table of 0.025. That's where this little diagram is here at the top. And now we're going to use the degrees of freedom in the numerator up here on these column headings, and then the degrees of freedom of the denominator on these row headings. All right, so that's the table we're using. So now we found the correct sheet in this table for the probability of 0.025. Then we look at the top and we find the degrees of freedom on the numerator, which is 4. Then we select that column, and then we look for the degrees of freedom of the denominator, which is 9. So we find that on the rows. And then when we find that row, at the intersection of this column and this row, you find the upper F value, which is 4.72. But again, what we want is the lower value. So we just take the inverse of the upper value to find the lower value. So the inverse of 4.72 is 0.2119. So now we have the lower value for the same probability as the probability at the top, and here's the upper value for an F distribution with 4 degrees of freedom in the numerator, in the denominator, and 9 degrees of freedom in the numerator. Okay, so with this, we've learned to use, I hope, and if not, make sure that you learn how to use table 7. All right, in the next recording, we're going to talk about the testing the hypothesis, where we compare two variances.